in the first part of the lesson, we have analyzed some field data and geophysical data about the geothermal fields that are around Amiata volcano. Now I'm going to show you a modeling done with TUF2, which is a code that allows modeling of porous and fracture media. So it's a dual porosity kind of modeling, and of multi-phase, multi-component fluids that and they calculate also the thermal aspects of a flow. This is a PhD thesis that was done at the University of Rome by one of my students. As we have seen in the first hour, in the first 2 hours, Amiata volcano, which is here. Can you see the presentation well?
Yes.
Yes.
This is Amiata volcano in southern Tuscany, and you can, from the topography, you can see very well, just northeast and east of Amiata volcano, the Siena Graben. That is a depression that was filled in with marine sediments that are now up to 900 meters above sea level. Amiata volcano is a structure, pretty tall structure, and the fields of Bagnore on the southwest of the volcano and Piancastagnaio on the southeast of the volcano is where are located. In the first 2 hours, still we saw the old geologic map of the volcano with all the lava flows, and in yellow on the right, the sediments of the Siena Graben, and to the south of the volcano in white, and then in green to the east, the impermeable rock formations that lie between the Amiata volcano and are on top of the Tuscan formation where the geothermal fields are located. And by working through all this fantastic work that was done by Cataldi in the early 60s, we have seen 3 main points that one should always look when observing geothermal fields. First of all, the heat source. Where is my heat source? Second, do you remember what was the second point?
The impermeable cover.
Good. The impermeable cover. You need an impermeable cover to avoid the rainwater to flow and cool down the geothermal system. The third point, do you remember the third point as well? You always have to think to the recharge. So recharge area, all geothermal system, the fluids of the geothermal system are always rainwater. So water must come from somewhere, go down, warm up and rise up again to warm up the rocks close to the surface. Hot rocks close to the surface are good geothermal fields. And these are the 3 aspects which are important. Why the recharge is important? Because if I start exploiting geothermal fluids by bringing them to the surface, and there is not enough recharge in the geothermal system, then the fluid dried out, and I get a dry well, a very hot well, but still dry. I cannot drive any temperature, any heat to the surface, and therefore my geothermal system is impossible to use. Now, there are cases in which there is not enough recharge, and that implies that I have to recharge the geothermal system. And one way to do it and is, for instance, as is done in the US in some of the geothermal fields, they bring the sewage system from cities straight into the geothermal system, recharging them with water. It doesn't really matter if there is any biological pollution, because at those temperatures, that pollution is gone. And therefore, sewage systems are really good for recharging geothermal aquifer. So now we go one step forward and we try to see the recent geologic maps that we did on Amiata volcano. Please tell me when you see it.
Yes.
Do you all see the new slide?
Yes.
Okay,
Yeah.
in this new slide, we were able to identify about 14 different lava flows and debris avalanches from Aviata volcano itself. And the old avalanches are the one in light green and dark green. And then you evolve to the purple lava flows, and then the light brown, then above that the dark brown, and then again the light green lava flows. You can also see a very large number of faults that cut the volcanic edifice. Therefore, through the volcanic conduits, one is here. Before they put no conduit here, but we think that this is a very good cone with the conduit itself. A second conduit, this is called La Montagnola, La Vetta, the third conduit. Through these three conduits and the main faults that cut the volcanic edifice, the water is able to percolate down the impermeable layer, pass through the impermeable layer, and feed the geothermal system. It's interesting to know that this light green area are not actually lava flows, but is where you find very large number of lava blocks right on the slope of the volcano, and showing that these lava flows have been dismembered by deformation of the clay-rich substratum. In this model, we have added the surface geology, and we have used the geology of calamite that we have seen in the first part of the section to put into the model the full geology that we find on the surface. Each formation which its own particular permeability. So this is, please tell me when you see the slide.
Yes.
Yes.
So this is the top of the superficial reservoir as seen from the maps, the topographic map that we saw this morning. And the volcano itself is right in this lower part. This is the place where the Miata volcano is located. And Poggio Zoccolino is this to the north, where you have the hot springs, but low temperature hot springs. And on the south, you have this area, and this area, which are actually the geothermal field of Piancastagnaio and Bagnore, here to the southwest. And on the second slide is the bottom of the superficial geothermal field. Now, Enel has not using the superficial geothermal field since the practically the year 90s. The superficial geothermal field was abandoned and they went to use the deep geothermal field. And this is the top of the deep geothermal field. The top of the deep geothermal field is still in the Toscan Formation, but in this case is our metamorphic unit, and only the lower part of the geothermal field is sufficiently fractured to have enough permeability to allow to extract geothermal fluids. The top part of the metamorphic Toscan Formation constitute a second impermeable layer, so that below at this depth here, which is 3 to 4 kilometer depth, you get temperatures well above 300 centigrade. Please interrupt if you have questions. Please tell me when you see the slide.
Yes.
So on the left-hand side, you see the geologic map we saw this morning with all the geological cross-section. And on the right-hand side, you see your geologic model. Each grid block is 500 meters in size, so the grid block cells are sufficiently large. However, there is a limiting number of cells that you can use in TUF2, and that is a few tenths of thousand cells. So there is not a lot you can do to discretize the geology, to very fine geology. You have to go to some coarse kind of geology. In red is the volcano. In white and gray are the more impermeable units, the chaotic complex, clayey chaotic complexes. In yellow are the neogene marine formations, rock formations, and all the other Ligurian units are in green and brown. Please tell me when you see this slide.
Yes.
Yes.
So we have to put a top boundary condition in the model, that is the pressure of the superficial freshwater aquifer. Through the work of Calamai et al., the one we have seen this morning, we have seen the topography of the superficial aquifer within the volcano. The aquifer outside the volcano and the topography of the aquifer has been interpolated based on data, if we had data, and topography. So wherever the topography is low, the aquifer is low. Wherever the topography is high, then the aquifer is high. So we have imposed, as it is in nature, sort of a waterhead all through the model, right at the top of the model. These are two cross-sections. Tell me, please, again, when you see the slide.
Yes.
So as you can see, our model goes down to 7 kilometers, where we have the intrusion. The intrusion is supposed to be impermeable, and therefore our intrusion, which has sort of a top below the volcano and goes down to the side outside the volcano, The volcano is in red and the volcanic rocks are in red at the top. This constitutes our heat source, and therefore we have an impermeable layer at the bottom with a heat source. This means that it's kept at constant temperature. So we have a constant pressure top boundary condition and a constant temperature bottom boundary condition. The bottom boundary condition is no flow. The top boundary condition instead allows flow to maintain that pressure. This means that if water by any chance flows down, like in a charge area, is actually asking for water from above. And so the model is able to give all the water that is needed to maintain the water table. This sort of reflects the average water table through the years that is maintained by rainfall and infiltration. Any question?
Yeah, I've got a question, Professor.
Please.
And how did you decide the dimensions of the cells?
We needed to have no more than 70,000 cells.
Okay.
So we were forced to decide. Now on the vertical direction, the cells change from 100 meters at the very top to about 500 meters at the very bottom. Of course, wherever I have less details, then I can use larger cells. But you can still see that you get the volcanic complex on top in red. You see on both slides, you get the conduit in red that go down. Then you get in yellow are the neogene formation, the marine sediments. In white are the impermeable layers. In white and light green are the impermeable layers below the volcano. Then the superficial geothermal field is in pink. These pink are the anhydrite that form the top of the geothermal field. And below is the Toscan formation, which is not continuous. And in yellow is the lower Toscan formation, the more permeable part, which is the actual geothermal field that is exploited today. And then in red is the high metamorphic units of the Toscan formation that go down to the intrusion. Did I answer your question?
Yeah, thank you, Professor.
If you are able to call me Andrea, that would be better. What do we have? So even if we have large cells, and that is something that we cannot avoid because of the limit in the number of cells that TUF2 can use. By the way, the newer version, TUF3, is a multiprocessor, so it can go up to millions of cells, so we would not have had this problem here. In the cross section to the left, you can see indicated the Bagnères superficial reservoir and the Piancastagnaio superficial reservoir. This is a sort of is looking south, northwest, southeast cross section through the Amiata volcano. And the other one instead, the one on top to the left, you can see the two columns, and it goes from north-northwest or west-northwest to west-southwest. Across the volcano, you can see the two chimneys, volcanic chimneys that are indicated in the cross sections that I've shown you by Calamai et al. 1970. And now I have to make a step in this. For this particular modeling, we have been used an equation of state, actually a number of equation of states that describe the thermodynamic behavior in a porous fractured media of water, that's the first component, CO2, that is the second component, and salt, NaCl. These three components allow to describe sufficiently well what are the major components of the fluids in a geothermal field. Now, the CO2 is supercritical, is in supercritical conditions above about 32 degrees and 700 meter depth, about 70 bars. Supercritical CO2 means that it has the behavior of a gas, however, it has the density, which means in practice the viscosity of a gas, very low viscosity, but has a density of a fluid, of a liquid, very high, much higher density than a gas. In this particular case, the density is in the order of 200, 300 kilograms per cubic meter. Then there is the water component, and that usually uses the thermodynamic properties of water, and then which is the largest part of the fluid. And then there is the salt. The salt is very important because in places in which the geothermal fluid evaporates, then the salt must precipitate, and by precipitating clogs up the fractures, reducing permeability. As you can imagine, this is not very simple to model. So the permeability is actually a function of the rock, but then the hydraulic conductivity becomes a function of temperature, becomes a function of pressure, which both influence the viscosity of the fluid, but also becomes a function of salt content of the fluid. And for the permeability itself, if there is salt precipitation, wherever there are gas phases present, then you may clog up the system. This is another aspect very important, because if by exploring your geothermal system you precipitate the salts, then you might clog up the system and you're not able to reduce the permeability, and you're not able to pull your fluid out of the geothermal system. So it's very important to try to avoid clogging of the fractures by salt precipitation. In many cases, people also use dilutant like acids, like sulfuric acid or chlorhydric acid. They pour down the wells to try to solve the calcium carbonate plugs and salt plugs that form within the fractures of the reservoir. Any particular question about the thermodynamics of the fluid? Is it all clear, this? So let's go to observe some of the results that we have found. Please tell me when you see the slide.
Yes.
Now, yes.
So in this slide, you see on the right-hand side the temperature bar. Blues and light blues are below 100 degrees. Yellows around 200, reds are above 300. This is the cross-section east-west. So Bagnore, the Bagnore geothermal field is west on the left, and the Piancastagnai geothermal field are on the right. And you can perfectly see that we can simulate relatively well the recharge of the geothermal fields. So the water from the water table flows down because it's cold and because of the overpressure given by the topographic relief. The water goes down and begins to warm up until it gets relatively deep, warming up very much, and then rising up relatively fast as hot plumes. And as they rise up, they warm up the rocks. And wherever there is an impermeable layer, they're able to warm up the rocks very close to the surface. And in practice, the superficial geothermal fields are these light blue areas to the west and to the east, and are relatively superficial. The deep geothermal fields are in the red part of the uprising plumes. This was the first time that the geothermal field of Amiata was modeled, and we got results that are relatively reasonable and comparable to the observations that we find in the field. Any particular question? You're all asleep. Please say yes or no.
No, no.
No.
Try to interact, because if you interact, I'm able to understand if you understand what I'm saying. Please tell me this new slide.
Yes.
Yes.
As you can see from the title, gas saturation after 4,000 years of simulation. 4,000 years of simulations, it takes about 24 hours of computing time for these relatively large cells. If you would go to smaller cells using TAF3, you can perhaps spend even 2-3 days for each simulation. What I want to show is that the column on the right, it tells you the gas saturation. So wherever is blue, you get only liquid phase. Wherever is yellow, you get slightly above 50% gas phase. And the gas phase is mainly constituted by water and CO2. Water vapor and CO2. Usually the water vapor is saturated with CO2, and there is a total equilibrium between the liquid water phase and the vapor water phase. And so you can see here how there is at around 50–60% gas saturation, what is called a heat pipe. So through the fractures and the pores of the rock, the gas and the vapor phase rise up at boiling point temperature, maintaining boiling point temperature. This temperature decreases slowly upward simply because the pressure decreases, but is on the line of a two-phase condition. So the temperature is controlled by the pressure. For any given, every time that the temperature tend to decrease, then part of the fluid condenses, liberating enthalpy that warms up the fluid again to keep the fluid at the same temperature. And this is called heat pipe, because you practically bring the same temperature all the way to the top. But what is even more interesting, you get areas, this big blob here, color of red, and a little bit like an S-shaped in the binary geothermal field. These are areas where the fluid is 100% gas, vapor and CO2. And this is exactly what we have, or we had at the beginning of exploitation in the Bagnere and Piancastagnaio geothermal fields, where you had the famous gas caps. And I think that this was a quite neat result. Another aspect which I found very interesting is that not in the Piancastagnaio geothermal field, but in the Bagnere geothermal field, at greater depth, you also have a 50% gas phase. So the deep geothermal field in Bagnere has a very large gas component and gas fraction. And this is actually what is seen also in the deep geothermal field of Bagnere, that the gas content, particularly CO2 in the geothermal fluids, is much higher than in the geothermal field of Piancastagnaio. Why I like to point this to you is because gases are really what you don't want in a geothermal field. And the reason is that gases do not condense. And if they not condense, they cannot liberate enthalpy to produce a larger power of electric energy. In a water vapor geothermal field, most, like 90% of the energy is not brought to the surface through temperature, but through enthalpy. And is through condensation of the vapor as it goes across the turbine that generates electricity, that I can recover this enthalpy and produce electric energy. Therefore, the plant does not work, or at least is not so important, the pressure that the fluid have, as much as how much vapor is contained in this fluid. And what you usually do is separate the water from the vapor, and you run through the turbine only the vapor. Do you have any questions? Would be nice to have some questions so I can drink a sip of water. You have no questions?
I have a question, if I can. So I see that in the previous slide you were showing that Enel was changing from the deep field to the one closer to the surface.
From the superficial to the deep.
From the superficial to the deep. So how is it taken, this kind of decision? So which is the way to decide
by
which
chance,
portion?
Yeah, by chance, they wanted to, they were afraid that at depth they would not find permeability. And in fact, all the wells that were drilled into the metamorphic complex before, they were dry. There was not enough permeability to run a geothermal power plant. So to drive to the surface enough fluid, consider that for flash, and I will explain perhaps tomorrow what a flash plant is. A flash plant is a power plant that runs on vapor. So condenses the geothermal fluids right past the turbine. To produce 20 megawatts electric, you need about 130 tons an hour of geothermal fluid. You need to pull out of the geothermal field 130 tons per hour. This is the rule of thumb. So it's a relatively large amount of fluid that you pull out as vapor. And so by chance, they decided they had enough money because it was state dependent, and they decide to drill one well down to 3 kilometers, 3,000 meters. And luckily they found enough permeability in the lower part of the Toscan section at this depth. And so that they started to develop the deep geothermal system. Why not to go above 300, 350 centigrades? Because if your steel is not strong enough to sustain and to be able to drill and to sustain those temperatures. You practically, it's very hard to do it and very expensive. Now there are ways to do it. There are materials that you are able to drill up to 600 degrees. So actually to enter into the magma, the real magma. However, these are very expensive and there are very few trials that have been done. And more than all, you don't have enough permeability. So most of these wells have been dry. So it was by chance, but it was a good chance. Did I answer your question?
Yes, thanks.
Any other question? Let me go to the next slide. Please tell me when you see it.
Yes.
Yes, now.
So it's not very clear, this slide. What I want you to concentrate is on the top surface, which is a top surface at 160 degrees, 150 degrees centigrade. And you see how much is articulated. And what you can see is that the recharge zone creates a hole around sort of a nanulus of hot water in the plume rising up. So this kind of rising cup of hot fluids are the Bagnore field on the southwest, and on the southeast, the Piancastagnaio field. This is another way of looking at, or a more interesting way is this next slide, and I would like you to tell me when you see it.
Yes.
Do you all see it?
Yes.
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 So on the left-hand side is the map that we have seen this morning. So the measured geothermal gradient on the surface. On the right-hand side is the calculated geothermal gradient by our model. And you can see how relatively similar the two are. Our model calculates slightly smaller, perhaps slightly smaller geothermal gradients than the reality. Also, our model on the right, it calculates a geothermal field that is not present, or at least apparently is not present, in northwestern part of the volcano, where the two lava flow tongues are present. Or at least these fields were not well known on those days. However, there is a recent project which is called Montenero that is trying to tap right into this potential geothermal field. I'm not sure if they're ever going to do it, but potentially by doing the modeling, we observed that there could be a geothermal field also northwest of the volcano, not just southeast or southwest. So this is sort of something new and something that could be very interesting, and something that this project Montenero is trying to tap into it. Why we think that there could be a geothermal field in this area? Because the topography of the area is the lowest around the volcano. And because it's the lowest, is the topography here is around 400 meters. Is 600 meters on the lava flows, while at Bagnor here is about, and at Piancastagnaro is about 800 meters. So down here is about 300 meters below that level, which means that geothermal fluids, the hot plumes, are forced to rise in this area, are forced to rise by the low topography. Any particular question? So if I would like to say let's drill a new hole at Amiata, I would really love to try down here in this area. I know that Enel has drilled around north here a deep well, but they found at about 3,000 meter depth, pressure that was so high, like lithostatic pressures. Do you understand when I say lithostatic pressure? In the rocks below ground, there are two kinds of pressure. One is the pressure within the fluid, and that is the hydrostatic pressure. The other one is the lithostatic pressure. It is the pressure between the grain rocks. Since the rocks have density larger than water, then the grain pressure, the pressure between rock grains, is usually larger at any given depth than the hydrostatic pressure. The rule of thumb is 2.5 times. So if at 100 meter depth you have 10 bars, then the pressure in the rock will be 25 bars. This is the rule of thumb. However, in this northern area, the pressure in the well, which means in the fluids, is lithostatic. And that is very dangerous when you drill, because it means that your fluid can lift up the rocks and erupt to the surface through your same well. Very dangerous condition, so they close the well right away. Any question?
Sir, how they manage to drill 4 kilometer, 4,000 meter? Because it's very difficult.
No, no, now these days, for instance, for shale gas, they're able to
Yes.
do to 5,000 meter in vertical and then horizontally 5,000 more meters.
Okay. In USA for shale.
In shales, correct, for shale gas. But there are various wells around the world that are down to vertically down to 10 kilometers. These are the most deep, the deepest one,
Okay.
are mainly experimental wells.
Yes.
Now to stop this very high pressure, what they use a very heavy mud, drilling mud. So they add to the drilling mud very high density components so they can raise the density of the mud to even to 3,000 kilograms per cubic meter. Any specific question? So we run briefly through the conclusions, and then I'm trying to show you what is being the effect of geothermal energy exploitation onto the first freshwater aquifer. So the conclusion of this modeling has been, in the natural state, the recharge comes from the volcanic freshwater aquifer. It's not written here, but of course it comes also from all the carbonatic outcrops that crop around at much larger distance of the geothermal fields. So the geothermal fields form at the base of the volcano because of the pressure gradient induced by high elevation freshwater aquifer. Gas saturated zone form naturally at the top of the geothermal fields, not geothermal fields were as domes covered by clayey rocks. You remember? Every now and then say yes or no.
Yes.
Yeah.
Okay. So please tell me when you see this next slide.
Yes.
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 So this slide, I put some color in it just to make it more clear. This is the map by Calamai et al. 1970, and is the topography of the freshwater aquifer before exploitation. So while drilling through the volcanic rocks, they have found first the freshwater aquifer. They recorded where the freshwater aquifer was. They also know the freshwater aquifer by resistivity studies. And all this was done before the drilling. So they're able to reconstruct fairly a decent map of the freshwater aquifer. Resistivity studies, by the way, are the #1 method for defining surface water aquifer. So even if it is a geophysical and not a direct measurements of the water table, here the resistivity study has been calibrated with a number of checkpoints, both in boreholes and also in mining, because there were a number of mines at Amiara. So it's a fairly good water table that goes from 600 meters above sea level on the west to 1,200 meters above sea level below the summit. Consider that the summit is 16,000 meters. So there are at least 400 meters of unsaturated rocks above the water table within the volcano. But then it drops down again to about 800 meters on the east, on the east and the north. Now, after the beginning of exploitation, and if you remember that the first thing they did, they were running CO2 right through the turbines to produce electricity. And by doing that, they were using the pressure drop across the turbine, no condensation, very little energy produced. But what they succeeded in was to reduce the pressure of the geothermal system so much to allow new fresh water to come in, warm up, and turn the geothermal system from being gas dominated from being water dominated. That is, a lot of water, a little bit of vapor. And then they remeasured, after this first exploitation in which they decreased the pressure, they remeasured the water table. And this is the water table that was measured. So the colors, can you see the slide here?
Yes.
Yes. Yes.
So where before in this area you had 1,200 meters of water table, the water table dropped by 300, 400 meters to 800 meters above sea level. Where you had here the water table at about 1,000 meters, the water table dropped about 400 meters to a minimum, 600 meters above sea level. And as you can see, it was created sort of a hole in the water table, a depression in the water table. And you can see also this depression going northeast through this area, where the contours have these big inflections. So this shows that through volcanic chimneys, through major faults, probably this is a major fault, and volcanic chimneys, a lot of the water, because they've dropped the pressure of the geothermal fields, a lot of the water starting to flow down into the geothermal system, lowering the level of the water table. Any question? It's pretty important that you understand this. Let me go back to the slide before. Can you see it?
Yes.
Yes. Yes.
So here, I will leave my cross right here, where I have above 1,200 meters elevation above sea level. This is the water table.
Okay.
And I'll put it back there. So in that, do you see the cross again?
Yes.
And the new map?
Yes.
In that exact point, I had above 12,000 meters elevation in the water table, and now I have about 800 meters, above 800 meters elevation in the water table. So your water table has dropped about 300, 400 meters. It's a huge amount. It's a reduction in pressure of about 30, 40 bars. What was the consequence? Most of the springs that were around the volcano, they dried out. So most of the villages, they run on the water from the water table, from the freshwater aquifer of the volcano. By the way, there are about 700,000 people that live on that water. So a huge amount were left without water. So what they did, they drilled draining tunnels in the volcanic rocks to try to tap the water left. And there are major drainage systems done in the southern part of the volcano, the western part of the volcano, and also the eastern part of the volcano. And so now they refed most of the water to the aquifer through this new drainage system. But the total flow rate through springs went from 1 cubic meter per second to about 0.6 cubic meters per second. So it dropped a lot. They lost a lot of water, but at the end, they were sort of able to save the aqueducts and the amount of water that people needed, but also the geothermal energy. So this is the first effect, first negative effect. These days, there is such a lack of fresh water that you really want to avoid draining so much surface water from the surface water table. So this is one of the first drawback is reduction of surface water resources while exploiting geothermal fields. Second point that I'd like to show you is that because of this reduction in pressure, about 30-40 bars reduction in pressure, the gases contained in the geothermal field start to rise up and to pollute the water table. One of the common gases of geothermal fluids is not only CO2, but also arsine, which is practically, once the gas arsine enters into the freshwater aquifer, becomes simple, get oxidized to arsenic and polluted the water. Many of the, sorry?
Which gas?
Again, the question?
You said two gases. One is CO2 and second is methane?
Arsine.
Arsine.
Is a gas made of the metal or the metalloid arsenic.
Okay.
But also other relatively poison gases are mercury. Very common.
Okay.
Mercury is very common, as it is antimony. In this particular case of Amiata, mercury is the most common, and simply because they were all among the world's largest mercury mines were here at Amiata. And these mercury mines were producing cinnabar, which is a mercury sulfur mineral, which is by itself inert. They don't react much. And the women of the Etruscans that lived in this area, they used it as to color their cheeks with cinnabar. But then they learned that by burning the cinnabar and condensing the vapor, so they produce SO2, and mercury vapor, and condensing the mercury, they were able to condense the mercury that become extremely valuable to extract gold from rocks. So since the Roman time, the mercury was extracted here at Amiata to bring the mercury to mine the gold from all the mines around, also northern Italy and Europe. So the second negative effect is that you start bringing hot gases into the aquifer, and among hot gases, vapor as well. So the water temperature of the aquifer started to increase. Let me show you another modeling that we did. Please tell me when you see it.
Yes.
Can you see it?
Yes.
Yes.
So,
Yes.
so this is a different model, perhaps more simpler, but very interesting. On the top, you see the water table measured by Calamai et al. 1970 before exploitation of the geothermal fields. At the bottom, at 7-kilometer depth, I have my heat source. And so you start seeing at the bottom, by radial Taylor instability, some hot plumes beginning to rise up. Now, this is 1,000 years before zero. I'm going slowly to run through this model. As you can see, the plumes are very many, but in time they become lower in number and larger in size. The light blue is about 300 degrees, and this is what you would like to concentrate on. And I anticipate that as the plume grows up, you will see that the high pressure of the aquifer below the volcano, the very high topography of the aquifer, will inhibit the plumes that are at the center to rise up into the freshwater aquifer. Sorry, made a mistake. I stopped it when I didn't want to stop it. Again, we run it again. Can you see it?
Mm-hmm. Yes.
Sorry, wrong. So run it again, the plume coalesce, and then they rise up, and they tend to emerge at the side of the volcano. This is a very clear picture. So the hot water comes down through the volcano to the bottom and then rises up into these plumes. And only the plumes that are at the base of the volcano are able to emerge to the surface. The freshwater aquifer is able to keep the geothermal plumes down below. And by doing that, inhibit the pollutant to rise to the surface. Other simulation, In this case, can you see this new slide?
See?
In this case, the top here is the measure water table after the exploitation, after the beginning of the exploitation, and after the reduction in pressure of the geothermal aquifer. You can see there is no more the high topography aquifer below the volcano. So now running at the beginning is just about the same, but then you see some plumes are at the base of the volcano, but some others rise straight into the volcano, into the lower part. You remember the hole, the famous hole that I've shown you, right into that hole of the volcano. And that they bring pollutant right into the volcano. Any question? No questions.
No, this is, if I can, because here I see the scale is like 1,000 of years.
See.
While if I well understood, the modification that you are talking about happened in few years.
Yes, but simply because you start here with all cold water aquifer. So you need thousands of years to actually develop the plumes. The real situation is slightly different because you start from the first frame and you end up into the second.
Mm-hmm.
So we have not done that simulation really, in which starting from the last frame of the simulation before and then see how it would influence that. And you will see that the plumes will be just shifted in, will be shifted right into the volcano. Let me show you a few other if I have. Devo farvi vedere. Oggi non do. Okay, this is it. Okay, let me switch. I will show you some more data. Oh. How come you don't see it? Preview.
No.
Oh, strange.
Yeah.
I
Now
don't. Let's see if I can see it now. This is, oh, it doesn't show up.
yes.
How come? Oh, I don't. Can you see it now?
Yes, I think.
What do you see? Can you tell me what you see? No, I don't. I
I
think
see your folders.
I see only the folders, but I actually want to see. Let's see. I want to show you the document, one of the documents in the folder.
No document.
No. I perfectly see that you don't see any document. Let's see. Let's try again. So I cannot show anything with preview in Teams. I can only see Microsoft Documents.
I think you can share your desktop maybe,
Yes.
and whatever is there it will be shown.
What about now? Can you see it, the document?
Yes. Yeah, we see.
It is written in Italian. Do you see a Google Earth map of
Yeah.
Amiata?
Yes.
You do see it?
Yes.
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 Good.
Yes.
So this is Mount Amiata, and in yellow, the pins are piezometers, which actually measure the level of the water table within the volcano. And so I will show him practically this red line, a cross section of the water table along this line. Please tell me when you see this.
Yes.
Yes.
So the lines that you are seeing are the measurement through time from July 2011 to November 2018 of the level of the water table. And as you can see, do you see the peak? The very high peak, the brown line is a piezometer which is above the piezometers which are black or China, the light blue. And as they have started using the new power plant, extracting more geothermal fluids from the aquifer, you see that the brown line, which is topographically above, is a piezometer which is above the black line. It just crosses. You see that? And the piezometer that is topographically above has a water table level that it becomes below the level of the water table of the piezometer that is actually below. In practice, This is, I show this picture, please tell me when you see it.
Yes.
So in blue, in Ball's blue, you see the level of the water table measured by a piezometer in December of 2018. And you see that the water table from the summit of the volcano goes down, then sort of flattens out. And then it goes up a little bit. It goes from 746 meters up to 747 meters, about a meter. It rises about a meter. So this condition is impossible to happen in an aquifer unless there is a well that pumps the water. If there was a well that pumps the water in the piezometer that is called NL4, right here, then you would see this kind of shape in the aquifer. But in reality, there are no wells. And that means that the water is going down into the geothermal aquifer. Is cut down by the depressurization of the geothermal aquifer. This NL4 piezometer is part of the minimum that was shown in the map measured by Enel. Okay, let me show some other data. This is exactly that same slide that we have seen before, with the direction that is reversed in this area. Let me show what has happened at this time when I get this kind of minimum. So the water table is through time, the water table through time here is from 2012 to 2017. And the water table, is the blue line and goes down, then goes up again, and then it goes down again. Now, whenever the water table goes down about 757 meters above sea level, then the temperature on the left-hand side, and is the pink line, it just goes up. Can you see it?
Yeah.
So you have the water table going down, and every time it goes down a given amount, the temperature of the water goes up. And then remains, it goes down again when the water table goes up. And then when the water table starts going down again, it rises up again, the temperature. And this is simply because vapor comes straight into the water table. It's not a lot of increase in temperature because it's between 10 degrees, say 10 and 12 degrees, this peak. A bit less than that, it's a bit less than 2 degrees, say a degree and a half. The second peak is perhaps only half of a degree, but I don't have here the later part of the system. So this means that the vapor must have entered the aquifer. to warm up the water. Consider that the water of the aquifer is maintained constant through time, because here you're very deep, is 100, 200 meter below ground surface. So there is no seasonal variation of temperature. And the temperature of the water is maintained by the temperature of the rock.